in 2.3 that we didn't get to that I want to talk about here. And then we're going to go in talking about 2.5, and the class after that will be kind of another like pause. We're going to practice a couple of specific ideas that I think is good to just take some time and settle in and practice, because they're a little bit more complicated, or at least like unfamiliar kind of situation that I want to kind of settle in and make sure that we have a good handle on before pushing forward, because there's, I think, just one more topic after today before I be looking at a test. So that's coming here relatively soon. So today, to finish 2.3, we need to talk about the squeeze theorem. So this will be the first named theorem that we have. The expectation here would be, at least from the AP perspective, this is a theorem you should be able to quote and use. So like the named squeeze theorem, and you should know the conditions that you need in order to apply it, and be able to state the conclusion of it to answer questions. So this is one that is probably going to be like close to memorized, is the expectation. Like they won't ask to like write down the squeeze theorem. I won't ask that, but I'd expect you to be able to use it and quote the name and know what you need to in order to use it and know what it gives you and be able to state those kind of things in words. So what the squeeze theorem says is that if we have a string of functions, f of x less than or equal to a g of x less than or equal to an h of x, so notice that that g of x in the middle is bounded below by this f of x function and bounded above by this h of x function. And that inequality holds at least in the neighborhood of some value a, except possibly at a, where one of them might be undefined or something. Yep. And what the squeeze theorem then says is that if the limit of f of x is equal to the limit of h of x, then the guy in the middle also has to have that same limit. So if the limit from the top is this one thing and the limit from the bottom is the same thing, the guy in the middle has to have the same limit. That those two functions are squeezing down on that middle function, forcing its limit to be the same as theirs. Does that feel okay? So that's in, like understanding like what is this thing saying, right? Like the symbols are the symbols, but like translating that into an English, and often translating into a picture is really what we want, right? Like, how am I actually going to use this? So let's look at an example. So it says, show that the limit as x approaches 0 of x squared times sine of 1 over x is equal to 0. So this is a show that, so I have to prove this limit exists. If I try to direct substitute that, I'm in a whole heap of problems, right? Because I'm going to have 1 over 0 inside of a sine function. That's basically taking the limit as sine goes to infinity. That doesn't exist, but it's saying this has to equal 0 somehow. So like a direct substitution seems totally inappropriate, and it's out. What we're going to do is we're going to use the squeeze theorem to do this. The hardest part about this problem is going to be building that string of inequalities, that f of x less than or equal to g of x less than or equal to h of x. But we're going to build that inequality out, and that's going to be the first step. So this guy here is going to be like my g of x in that above. Okay? So everybody cool with that plan? All right, now I need to build this out. So when I'm doing these kind of squeeze theorem problems, if it doesn't give me the string of inequalities to start with, I really hope I have one of two things in my function somewhere. I want a sine or cosine. That is super handy to build my string of inequalities from, and I'll explain why in a second. Or the square root of a difference of two squares. You know, like I have the square root of 4 minus x squared or something. Something like that is also excellent starting materials. We'll explain why in a minute.
What units is this, 2.4?
This is 2.3, we're just finishing it.
Okay, cool.
Yep.
Thank you.
No problem. Everybody good so far? So the trig piece is what I want, because I remember from last year in trig that sine of x is bounded above and below by 1 and negative 1, right? The outputs of sine x always have to be between negative 1 and positive 1, right? It doesn't matter what I'm taking sine of. So like sine of 2x, still stuck in between negative 1 and positive 1, right? Sine of 1 over x, still stuck in between negative 1 and positive 1, right?
This is just recap. It can't be like sine of 1.5, then it's outside the bounds.
Sine of x cannot be 1.5, correct. Yep. Does everybody feel good so far? So this is like my starting, you know, like this is kind of like my F, this is going to be like my G, and this is going to be like my H, and I'm going to build this inequality into F, G, and H, right? To just kind of give you an idea of where I'm going with this. So far, I've got that part, right? Now I'm going to multiply every part of this inequality by x squared. How do I know that's not going to flip an inequality, right? Sometimes when I multiply both sides of the inequality symbol flips.
Not negative.
Yeah, x squared is greater than 0, or greater than or equal to 0 always, right? That's why we are allowed to do this, but that's the next step. So this guy now is my f of x, there's the g of x, and that's my h of x. So I built my set of inequalities, my string of inequalities. That's the hardest part. Yes.
When it says, for this week's theorem, when it says, so when x is near a, what is a? Is that just where the...
A is 0 in this case.
Okay, cool.
That's like my a. Whatever the x is approaching.
Okay.
So to do the squeeze theorem, I just need to check the limits of h of x and f of x, which are both, they're just direct substitution. We get 0 for both of them, right? So I would say since negative x squared is less than or equal to x squared, negative x squared is less than or equal to x squared times sine 1 over x, which is less than or equal to x squared, and the limit as x approaches 0 of x squared equals the limit as x approaches 0 of negative x squared, which is equal to 0. The squeeze theorem states the limit as x approaches 0 of x squared times sine 1 over x is equal to 0. And we're done. But that's the idea. Yes?
So if, like theoretically, if the x squared, if there was more tacked onto the x squared, would you have to multiply by multiple things to get to the end result? Like
You might, or you might have to add things to both sides. Like if this had, plus 7 or something at the end, then you like add 7 to each part, or if it was like log times, you know, multiply a log term on or whatever you need. But yeah, that's the general setup. We like having a sine or cosine piece on there because it gives us an excellent starting place, right? It gives us that inequality to start with. Go ahead.
We were also saying about the difference of perfect squares.
Yeah, like if I have a square root of something like this. So if you think about the graph of this thing, it looks like that, right? Where this is like -2 and this is +2. So if I have like the square root of some difference of 2 squares like that, it like ready makes the string of inequalities that I need, and if there's other stuff tacked onto the outside of that, I can just multiply and add on, and like, but that's my starting string. Getting that starting string is the trickiest piece. Those are your two that you're hoping to see, is a sine or cosine, or the square root of like a difference of 2 squares like that. And those are your starting points. Those would be your starting points to build that out. Now, a lot of the time, you know, on the AP exam, they'll just give you the string of inequalities, where all you have to do is take the limits of both ends and check to make sure they're equal. Not hard, but you have to recognize, oh, that's a squeeze theorem problem. I need to do that. Multiple choice question, expect to see that. They'll give you the string of inequalities and ask, what's the limit of, and they'll give you something like, they'll just call it like f of x in the middle. They won't even give you a function there, so you can't even try to take the limit of it directly. You have to squeeze theorem it, there's no other way around it. So it forces you to recognize it as a squeeze theorem problem. What do you say if the two, the limit of your f and h don't match? What would you say? You don't say limit doesn't exist.
Infinite.
You don't say it's infinite, it's not undefined. It cannot be determined from the information given.
Can't say.
You just can't say anything about it. I don't know what it is. Does it exist? I don't know. Could be, maybe, I don't know. The string of inequalities you gave me is inappropriate for me to be able to say anything about this. Say, can't say. Can't say. Not that I don't know, it's that you can't determine it from the information that's given. It's like, no one could do this, not just me. Does that feel okay? So that's the squeeze theorem in a nutshell. Does everybody feel okay doing that? I have some examples for us that we'll do next time in class to really kind of pound this away. There's a little bit of homework at the end of 4.3 using this. Perhaps 2.3. You know what I meant. That hits on this, but we'll do some real practice later on because it's something that we just need to be comfortable using and recognize the situation when we see it. So we'll do some more example in class next time and just like settle in and let you guys get some immediate feedback on stuff. Sound good? We're going to go on to 2.5 then. And we're going to start by defining what we mean by continuous at a point. And just general continuity then afterwards. So you guys have talked about continuity probably in Algebra 1 and Algebra 2 and pre-calculus, and probably defined it kind of informally as like, if I can draw my graph without picking up my pencil, the function is continuous, right? Something like that. What we want to do is take that informal definition and translate it into something that you could prove. So I need to tighten up that definition. So we'll start with continuity at a point. For a function to be continuous at a point, the function has to be going in to the point, has to be coming out of the point, and has to be defined at that point. Everybody agree?
Yeah.
That means you can't have a hole, you can't have an asymptote, you can't have a jump. everything comes in, comes out, and it's there. Do you agree? So the coming in, that's the left-hand limit. The coming out is the right-hand limit. Being there is the function defined at that value. So remember, if the left-hand limit equals the right-hand limit, that says the limit exists and has the same value. So our definition of continuity at a point becomes just the limit as x approaches a of f of x equals f of x. It's essentially the direct substitution rule. So if you go back to section 2.3, our direct substitution theorem says we can do that for polynomials, right? If f of x is a polynomial, the limit as x approaches a of f of x is just f of a. That tells us from this definition then that all polynomials are continuous everywhere, which we knew, right? That same theorem in 2.3 said that for rational functions, where a is in the domain, the limit as x approaches a of f of x is equal to f of a. So we can say that the same thing about a rational function, in between its asymptotes, it's going to be continuous. Right? And that makes sense. That matches all the pictures we've seen, like in between its discontinuities. Should probably say discontinuities, because you could have a whole result in a rational function. But in between its discontinuities, it'll be continuous. Does everybody feel okay with that idea? So let's look at a couple of examples. So again, the definition says f is defined, the limit exists, and the limit is equal to the function output. So let's take a look at this graph here. We're asking at what values, or what numbers x, is the function discontinuous in y? So where do you see discontinuities at? What values of x?
3.
So 3, 5, 1. Okay?
It's not good.
Right, so what part of 1, what part of the definition of continuity does x equals 1 fail?
The limit doesn't exist.
Not the limit. The limit is fine. The limit exists. It's f of a is undefined, right?
What do you mean by that?
So remember, our definition of continuity is the limit is equal to f of a.
Yeah.
So the limit exists. The right-hand limit and left-hand limit are going to the same spot, but f of a, the value of the function there, is undefined,
Okay.
right?
Is it because
Because it's an open circle, so there is no y value for that x, right? If I plug 1 into f of x, I get undefined. There's no y coordinate that goes with it. Everybody okay? If I look at 3, what's the problem in 3? Oh my God, come on. Whatever. I hate you. What's the problem with 3?
they're not going to be the same thing.
Okay, which means what part of the definition of continuity fails? The limit doesn't exist because the left-hand limit and the right-hand limit are not equal. Right? The function is defined there, right? F of 3 has a value. It's this y coordinate right here, but the limit doesn't exist. Right, good? And then 5. What's the problem with 5?
Yeah.
Not quite the same as 3. It's close. Because f of 5 exists. F of 5 is this value. The problem is that it's not equal to the limit, right? So there's 3 kind of ways that this can fail, right? It can fail because f of a is undefined. It can fail because the limit doesn't exist. Or it can fail because the limit is not equal to the function. Does that feel okay? So those are like the 3 ways that'll fail. So far, so good?
Mm-hmm.
Okay. So here it asks, where are the following functions discontinuous? So if I look at A, I recognize that type of function as a rational function, right? We just got done talking that the rational function should be continuous at all values of x in their domain. What values of x are not in the domain of that rational function in A? 2. Why is that, Adriana?
Because it makes 0.
Makes a 0 denominator, right? Everybody can see that? So what's going to happen, hopefully you recognize that the numerator is factorable. So you can say that, right? Is that correct, what I've written? Not quite. What's wrong with it, Mark? I see you shaking your head. I have to state the restricted values, right, which should be like x not equal to 2. You guys remember that little picky piece in pre-calc where it's like we reduce the rational function, we have to list the restrictions afterwards? Yeah, maybe. Some of us are like, yeah, I did that. Some of us are like, I don't think I ever did that. And I'm like, well, probably found that out on the test. Someone had a comment or a question? No? Still doing okay? So if I look at that then, f of 2 is undefined, but the limit as x approaches 2 of x plus 1 is just 3. So there you're seeing that definition of continuity is certainly failing, right? So x equals 2 is our discontinuity. And what type of discontinuity will that be, where the limit exists, but the function is undefined?
The first one we're talking about.
That's a whole, right? Yep. Ready for good? Let's look at B here. Okay.
So for examples B and C, those will never be continuous. Those will never be continuous functions.
Piecewise functions can absolutely be continuous.
Oh, they can?
Yep. They can absolutely be continuous. So never is a strong word in mathematics.
Yeah.
So unfortunately, if I just take, for example, if I take the first piece to be x squared for x greater than 0, and the other piece to be x for x less than 0, it's going to come in like this, and then go like that, and connect.
Okay.
So they will be continuous.
That makes sense.
Yeah, so it's not difficult to take a piecewise function and still make it continuous.
Yeah, I just thought that.
Yep. Yeah, you want to think it one thing, but it's not. All right, so if I look at, I don't know why I just jumped. If I look at this piece, oh my God, stop already. If I look at the 1 over x squared, rational function, right?
Yeah.
Continuous everywhere over its domain. The only value of x not in its domain is 0. That's fine, because it's not in this piece of the piecewise anyway, right? So f of 0 definitely exists.
Is it just a point then?
Ooh, that is a thick boy I got going there. Dial that down a little bit. Well, we got to check what the limit as x approaches 0 of 1 over x is. So when I plug 0 in for x, I'm going to get 1 over 0, right? Everybody agree? What's going on there then? What's that telling us the limit is equal to? So, filling in the delta mass at the start of the year, they would have accepted that answer. I want to differentiate between does not exist and infinity. So is this does not exist, or is this going to be positive or negative infinity?
Positive infinity.
Positive infinity. Okay. So Frankie, not that you were wrong. It just depends on like what we're saying does not exist means. So I want to differentiate between limits that equal infinity or negative infinity and does not exist as two separate things. Does that feel okay? So this is positive infinity. If you think about the graph of this, that's probably the best way to think about it, because it's going to go both ends up like this.
But it's never gonna reach 0, so it's always gonna go towards infinity, which makes it.
Yep. So here we have our graph would basically be looking, and then like something like that. See?
For the discontinuities, are there like different kinds of them, like to differentiate between?
There's really three.
There's three.
There's an infinite discontinuity, like at an asymptote.
Okay.
There's a jump, or one end doesn't match up with the other. And there's like a removable, where there's like a hole, or like a hole with a point.
Okay.
So again, those are not equal. So this is telling us x equals 0. Everybody's good still? Let's kind of keep on chugging here. What if we have, we'll take that first thing that wasn't continuous at 2, and let's fill in a value there at 2. Well, we know f of 2 is 1, right? That's easy to see. And we just need to check the limit as x approaches 2 of this guy. Now we did this before, right? That this was just x plus 1. So is this continuous at x equals 2? No, because the limit doesn't equal the function. So we're still discontinuous at x equals 2. This guy, this is a notation that your textbook defined at some point. I didn't bother to define it for you. It's beyond the expectation of either myself or the AP that you'd recognize what that means. But we'll talk about it for a minute because it's on the paper and somebody's probably curious. That's the notation for the floor function, which is essentially just the round down. So like, if I have 0.2, the floor function rounds that down to 0. If I have 0.75, the floor function rounds that down to 0. It basically just cuts off the decimal and leaves you with the whole number part. Okay? So what you have is like a step function that goes from like 0 to 1, and then like 1 to 2, and then looks like that. If the brackets went the other way, if they went like that, that's the ceiling function, and it rounds up instead. It's like 0.1 would round up to 1, etc., etc. Is there discontinuities on that? How many? Infinitely many. Can we predict where they happen? Where do they happen at? Every integer value of x, right? There'll be a discontinuity of 0, 1, 2, 3, 4, -1, 2, 3, etc. So we would just say that.
What is that? Because that's not absolute value. Right?
Wait, what did you just say?
So I wrote that x is an element of the integers. So the little e symbol is like the member of the set. And this is the symbol for the set of integers. So the positive, negative whole numbers, including 0. So that's a common notation. Should probably be familiar with our, like, you know, like symbols for our. For our 5.
I know all real numbers.
Okay.
That's about it.
C is the complex. So like 3 plus 2i.
Oh, okay.
Okay.
Got it.
Q is the rationals.
Okay.
So Q is short for quotient. Like anything you can write as a fraction. Z is the integers.
Like 1, 2, 3, 4.
And then -1, 2, -2, -3, and then 0.
Okay.
YZ. In German, I think integer is like Zinteger or something.
Oh.
Remember, mathematics is a like global discipline. And N is the natural numbers. In this class, the natural numbers are just 1, 2, 3, 4. You're counting numbers. Yes, sir.
So, for D, what does that mean again?
That's the floor function. It just like the rounds down. So every decimal, it just rounds it down to the nearest whole number.
Is that on our calculator?
Nope. No. What's up? You're good?
Yeah.
Okay. Again, like, I won't test you on this directly, but you'll see this notation pop up pretty frequently. Don't be confused by it. That's all they mean. They're just talking about sets of numbers. The most common one is probably Z or R, but that's all. These are just the graphs of those things that we looked at before. So again, like confirming what we did symbolically, visually. Now here's a question. Let's say we want to talk about the function the square root of x. The graph of that just kind of looks like this, right?
Yeah.
Should this be continuous over its whole domain? What do you guys think? We would want to say that, right?
Yeah.
We draw it all with one pencil stroke. What about this point? What's the left-hand limit at that point?
Anything less than 0.
It doesn't exist, right? Because the function doesn't come into 0. There is no left-hand limit there.
Isn't the square root of 0 to 0? Or does that not exist?
Right, but the left-hand limit is the values less than 0 coming in. None of those exist. Emma? Sure. So we want to adjust what we mean by limit that continuous at a point and limit existing for cases where we have like a closed interval of the domain. So we say that a function is continuous from the right if the right-hand limit is just equal to f of a, continuous from the left if the left-hand limit is equal to f of a. So then if we talk about a closed interval, like this guy, we say it's continuous on the interval if at the end point it's continuous from the right or left, whatever's appropriate. So it's just us making a contingency for these closed interval functions to say it's continuous over still at that where that point is solid. Everybody's okay there? now if it was like this, and it's open, that should not be continuous at 0, right?
Yeah.
We wouldn't want that because it's open circle there, that doesn't exist. F of A doesn't exist, so should not be continuous there. You guys see the distinction? So that's all this extra definition is doing. It's saying, like, for these functions that have closed intervals, you don't need left-hand and right-hand limit. You just need this end of this, which end you need, whichever limit, end of the limit you need going into the interval, right? You don't need the other end. Does that feel okay? So just kind of like covering a contingency. So as an example here, it says show that the function f of x equals square root 1 minus x squared is continuous on the interval -1 to 1. So to do that, we need to do 3 things. We need to show it's continuous at each endpoint, and then continuous everywhere in the middle. Everybody's okay with that? So, there's like 3 checks that we're going to do. Is everybody okay with the 3 checks?
Yeah.
Again, this is just x equals a, where a is some number, and actually we should say the open interval because we're doing the endpoints already. So somewhere between -1 and 1, not including those endpoints. And I do that as just with an arbitrary a, so it hits all of them at once. If I just pick 0, all I've done is I've shown it's continuous at 0. To get everything in between -1 and 1, I have to do that arbitrarily, because how many numbers are there between -1 and 1? Infinitely many. I'm not going to be able to do it one at a time. Right? I got to do like a general one and knock them all down at once. Lucia.
So if we're not sure, like in the square root, we're not sure what the 2 numbers on either side could be. Could we like graph it and see?
Well, it should tell you the
it'll
interval,
tell you. Okay.
right? Like if we're showing, this says show, so it's going to tell you exactly what you need to do.
Okay.
That this is continuous on the interval. Now, if it said over its domain,
Yeah.
that's rude, because now you have to find the interval yourself. But yes, looking at the graph would be perfectly reasonable. That, assuming you have access to a calculator. Because you always have to remember that, like on the AP exam, and on my exams, you'll have a calculator portion and no calculator portion. Okay, so here, if I do f of -1, I just get 1 minus square root 1 minus -1 squared, which is just 1. Is okay? And then I need to look at the limit as x approaches -1 from the right of 1 minus square root 1 minus x squared. Now, to be clear, we haven't expressly shown that I can like do a direct substitution on a radical function like this. You can. So I'm going to just do that to do this. Is that okay with everybody? We're going to get to the theorem that I would need to do it in just a second. So I'm just going to jump ahead, but I get the same thing. I just get 1 when I plug it in. It's the same as up here. I do the same check over here now. And I get the same thing. Oops. Everybody okay? This is very anticlimactic, Mr. Kulik. It's like, well, it's a show problem, guys. Like, did you expect something, you know, like this to get complicated or something? It's only so much we can do. Now, we're approaching, since this is the end point, we need to approach -1 from the left, right? Because that's the right end of it, so it's got to be coming in from that side. And again, you direct substitute, you end up. To go from -1 to 1, the left end you have to come in from this side because the stuff lives in between there. So the left end you're doing the right limit, and the right end you're doing the left limit. But that's all that's so anticlimactic, but it's like those are the three things you have to check. No big deal. And we're gonna knock out doing this check real quick here. So that will eventually become trivial. All right, super useful set of theorems. No one will ever ask you to quote these, but you sure as heck would want to be able to use these. It just says that if we have two functions that are continuous at A, f and g, if I add them together, that new function is also continuous at A. If I subtract the functions, the new function is also continuous at A. If I multiply them together, the new function is still continuous at A. If I multiply them by a scalar, just some constant, that new function is still continuous at A. If I divide them, that new function is still continuous at A, provided the denominator is not equal to 0 at A. You guys okay with that? So the same rules for limits. Hey, that's nice. Shouldn't be a surprise though, because our definition of continuity was basically the same as our limit, right? Theorem 5 says any polynomial is continuous everywhere across its entire domain. It's continuous for all real numbers. You knew that. Any rational function is continuous wherever it is defined, i.e. it's continuous across its domain. So like, you know, if I have 1 over x, that's continuous from -infinity to 0, and then from 0 to positive infinity. Right? Everywhere except for that where that asymptote is. Does that make sense? Even better! Theorem 7. The following functions are continuous for every number in their domains. Polynomials, rationals, roots, trigs, inverse trigs, exponentials, logarithms. Every type of function you studied so far, continuous over its domain. You get that for free. You can just state it. So it'd be like, this thing is continuous here because it's a polynomial. Done. Don't have to do any limits or anything else. Just quote the type of function it is and say it's continuous there. Unless the directions say, like, specifically use the definition of, you know, continuity at a point to show that this thing is continuous. And that's a different thing, but. All right. So let's look at this example. It says f of x is the natural log of x plus tan inverse of x over x squared minus 1. We're asking, where is this continuous? When I look at this, I see 3 continuous functions, right? So I know that the sum, difference, quotient, product, scalar multiple of continuous functions is still continuous. So to figure out where that's going to be continuous, I just need to compare the domains of these 3 functions. And then account for one other thing, which would be a 0 denominator. So if I have the natural log of x, what's the domain for the natural log of x?
Zero.
What's that? Greater than 0 is correct. So 0 to positive infinity, I'm going to write it as interval notation, but greater than 0 is correct. Remember, you can't take the log of a negative number, can't take the log of 0. If you're ever curious or not sure, can't remember, and you have access to your calculator, you type in log of any negative number, it's going to spit back a domain error. If you do log of a 0, it's going to spit back a domain error. It's a nice way to check to make sure that you got it. I'm going to skip the tan inverse for a second. X squared minus 1, what's the domain on that? All real numbers, right? Why? It's a polynomial. Remember, it's the domain for tan inverse.
It does that little weird thing.
Does that weird thing. Yeah, so most of us probably don't remember, right? That was something you would have learned last year in pre-calculus, but you probably forgot shortly thereafter. Do you remember what the graph, one period of the graph of tangent, what does that look like? Kind of looks like that, right? Does that look familiar?
That looks familiar.
So if I want the inverse of that function, I just reflect that across the line y equals x, right? So that's tan inverse. What's the domain of that function? All real numbers. Feel good? So again, I'm not going to memorize a lot of these things. What I'm going to do is like take something that I know, like what the graphs look like, and that inverse property that I can just like draw the graph of the inverse and that'll be good enough. You know what I mean? I'm going to try to, me as a math student, try to memorize the minimum, and like I'm going to use the definitions that I have to know to get these like little piddly memorization things like, what's the domain of tan inverse? Like, heck, I don't know what that is right here. Let me draw a picture and figure it out in a second. That's the way I like to do it.
So then the overall domain of all of them, since it's where like f.
Well, hold on. And then we have the denominator cannot be 0, right?
Oh yeah.
So what values are excluded from that?
1.
And?
Negative 1.
Okay. So to find my domain for the whole thing, I need to look at the intersection of these three sets and then remove those x's. Do you know how to do the intersection of a bunch of sets like that written in interval notation? Your calculator probably won't help you there. This should be a problem you can do without a calculator, ideally. Let me show you the easy way to conceptualize this.
2 by 10s or something.
What I'm going to do is I'm going to draw these three domains on the number line. So here's my number line, right?
Oh, we did this one.
If I draw 0 to positive infinity, that's like that, right? If I draw all real numbers, it's like that, right? If I draw all real numbers, it's like that, right? If I want the intersection of these, it's going to be the overlap of all three of them. So 0 to positive infinity.
Why is it besides one?
What's that?
Oh, but if it's negative one, then we should, isn't it one?
And hold on, and then we have to count for this, right?
So it's not 0.
So -1 and +1, we have to chop out of there, right?
Where did you get the, doesn't that say -1?
Oh, should be plus or minus, excuse me.
Oh.
My bad.
Okay.
So if I do that, this becomes 0 to 1, and then 1 to positive infinity. And that's my answer. So again, to do this, I just look at the domains of each separate piece, union all that stuff together, and then subtract out of that anything that gives you a 0 denominator.
That makes sense.
Notice that the -1, 0 denominator didn't matter because -1 wasn't in the domain anyway. So it didn't really matter that that couldn't happen because it couldn't happen from the top already. The log took care of that possibility. Does that feel okay? We hinted at this way back in 2.2, or 2.3, I don't remember, I hinted at this though, that I can push a limit inside of a composition. And I said it wasn't always true. Here's the conditions in which it is. So it says if f is continuous at b, and the limit as x approaches a of g of x is equal to b, then the limit of f of g of x is equal to f of b. In other words, as long as those domains match up, I can push the limit inside of the function. Yes?
Use restroom.
Sure.
Thank you.
Okay. So if I look at this problem, if I try to do a direct substitution on that, I have arc sine of 0 over 0. So what I can do is push this inside and deal with just the limit of 1 minus root x over 1 minus x. You remember arc sine is the same as sine inverse, right? Yeah. Okay. Worth stating. So how am I going to do this limit here now? What would we do? Multiply by the conjugate. Totally reasonable answer. There's a shorter way for this particular one. No. So when I look at this, I look at the bottom and I see a difference of 2 squares. I see 1 minus root x, 1 plus root x. Yeah, look at it for a second. Now this is subtle, and again, multiplying by the conjugate definitely will work. It's just going to be more writing. And on a timed AP exam, any little tricks that you can kind of build up and put into your toolbox that eliminate having to do a bunch of computation are to your advantage, so you can spend 5 minutes on some problem that's really difficult because I saved 6 minutes along the way on a bunch of problems where I found the quickest way to do them. So again, not necessary to see that. But, boy, that makes it a heck of a lot shorter than multiplying by the conjugate, because we can see right away that this is just going to be like 1 over 1 plus root, oops, got my limit. Limit, this goes to 1 of 1 over 1 plus root x. And now I can direct substitute that So arc sine of 1 over 1 plus 1. What's arc sine of 1/2? It's 30 degrees, so like pi over 6. Do they expect you to be able to do that? In your head, with no calculator. I know. The way to think about it, sine is x or y on the unit circle. Y. If y is 1/2, that's gonna make the smallest angle, right? That's 30 degrees or pi over 6. That's all I'm doing. To do it in my head. But it really should be like plus 2 pi k, where k is an integer and the other one is 5 pi over 6 plus 2 pi k, where k is an integer. Which stinks, right? Because you have to say everything coterminal to it. And then the other place where sine is positive is in the second quadrant. So that's the hard part, to do that. The 30 degree, getting to 30 degrees should be doable. You think about it for a second, draw yourself a little picture on the unit circle. Again, like, I don't have the unit circle memorized, but I can picture it in my head and where stuff has to go, and like, okay, that's that, and that's that. Because I just don't have the mental energy to like rote memorize stuff. I hate rote memorize. I want to just like reason it out, like get the big concepts, and then that allows me to fill in all the details. I don't have to muck around with memorizing details because I understand the big concept. So similarly, if you compose two continuous functions, that composition will be continuous provided that the domains match up the right way. In general, the stuff that you are doing, the functions you've seen so far, you can push limits inside of compositions all day long. I will show you some examples next time of like places where that falls down, where that doesn't work. But if it's like written out functions like f of x equals e to the x plus 5 or whatever, like push limits inside of that stuff all day long. Like you won't run into domain problems there. It's really hard to build examples where that's a problem. Where it could happen is if you're given graphs. And that's the way I'm building. That's the example I'll show you guys next time of where that composition, pushing the limit inside the composition, you have to be really careful. Last topic for today, coming right down to the end, is called the intermediate value theorem. Once again, this is one where the AP is going to expect you to be able to use this and quote this by name. So the intermediate value theorem says, suppose f is continuous on a closed interval. That's one condition. And let n be some number between f of a and f of b, where f of a is not equal to f of b. That's condition 2. So you have to show two things. F is continuous, and then the number n that you're looking at is between two of the y values, specifically the endpoints of the interval. Then there exists an x value, a c, on the interval from a to b, such that f of c is equal to n. The intermediate value theorem does not tell you how to find that c.
It
just says there is one. Doesn't even have to be unique. There could be many such c's. So this is the idea, okay? So if I have I have the point a comma f of a, I have the point b comma f of b, and I have an y value n that's in between. If my function is continuous, I can draw, oh come on. Any way I draw that function, I have to cross n at least once. Right? Any place I cross n, that's going to correspond to some c. That's what it's telling you, is that there's a c then. Yes.
So that you have more than one C.
Absolutely, yes. The C does not need to be unique. It does not, this intermediate value theorem doesn't tell you how to find C. What the value of C is simply proves that there is one.
Well, if you cross C, there's gonna be two, because you have to, oh, no.
It could just, you
You could just go over it and get it.
okay?
Show me.
So let's do this example and then that's gonna be it for today. Yeah, I think I have enough time for this. So it says, show that there is a root for the equation, yada, 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 between 1 and 2. So when I read this, this is my f of x. This is my n. This is my a, and this is my b. Is everybody okay with me just filling in the symbols to match up with the theorem that's stated?
Yeah.
So first thing I need to show is that f of x is continuous. Oh my goodness. Why is f of x continuous? Because it's a polynomial.
I know that's right.
Notice that I didn't have to prove continuity here. And I should probably say continuous everywhere. Specifically from 1 to 2, but everywhere is good enough. So I then observe that f of 1 is going to be 4 minus 6 plus 3 minus 2. That's equal to negative 1, which is less than or equal to n equals 0, which is less than or equal to f of 2, which is 32 minus 24 plus 6 minus 12, or minus 2, which I think is 12. There's a lot of number talking.
Did you get the n equals 0? N 0. Oh, okay, yep, gotcha.
That's the y value I'm concerned with. So, by the intermediate value theorem, there exists, or if you feel like it, if you feel like doing math symbols, the backwards capital letter E means there exists a C between A and B such that f of C is equal to n or is equal to 0.
Wow.
Good afternoon, Notre Dame. Let's pause and take a moment to reflect on our day.
One more
Lord,
second.
have I allowed your hope and joy to triumph over my worries? God, I again ask that you please give me the ability to lay down all my burdens and worries I have for my life, my family, and my future, so that I may overflow with your hope. Amen. Teachers, you may dismiss as you are ready. Have a great day, Notre Dame, and God bless.
Just one couple of things. So IVT is an abbreviation you can use. The AP will recognize this as intermediate value theorem. Save yourself all those letters. The most common mistake students make when using this is they forget to prove the continuity. For next time, the homework quiz is going to cover showing things are continuous. Okay, so those are going to be the problems. Either continuous at a point, or continuous over its domain, or both. That would be the next homework quiz.
Okay.
Okay? Everybody feel good?
And then that homework's due Sunday.
This homework from 2-5 would be due Sunday at midnight. Yes.
So about the homework from that's due on Monday, right? Or
Yes.
Sunday. If I, so when I upload it to OneNote,
Yes.
so I just take a picture of it, put it in my
In your homework tab?
tab,
Yes.
and then should I send you an email when I do it?
Yes. Perfect.
And then the delta math, was it just that first entire unit that was due?
Yes.
Okay, so I'm done with that. Then I just have to upload the pictures. Okay, I got it.
All right. Perfect, Sam. Thank you.